afternoon. What is that? Happy Halloween. All right, ready for trick or treat? Let's get to the lecture first, right? Anyway, glad to see everybody, and glad to see lots of people who are interested in our distinguished guest this lecture today, Dr. Mark Pederson. So it's really great to look at the Mark's CV, and it's very unusual career path. And also, I guess for those of you who have met him, should be really good exercise to think about how would you, as a junior faculty, or middle career or senior, to talk about program managers. So Mark, after his PhD from University of Minnesota, you grew up in Minnesota, Wisconsin medicine, right? So he went to Naval Research Laboratory, and he made quite a lengthy time there, from all the way beginning with postdoc and then become a section head. That's the first time I also saw beyond the DOE labs, right? We one time removed that layer, but you were there as a section head. And then he decided to help more people by going to National Science Foundation as a program manager for many years. And after that, he went to actually DOE, basic energy science, as also a program manager. So I don't know who some of you in chemistry did have interaction with him prior to his time there. So anyway, so he was a program manager over there for more than a decade, right? And then finally he wanted to go to Joy Place, University of Texas, El Paso. So what excited me about is, over all this lengthy years of government service, he managed to keep publishing and have very high citation with everything. This is something extremely impressive. I mean, I would never be able to do so. So today he's going to talk about something related to chirality and symmetry, and it would be very exciting because that's, I assume, related to Energy Frontier Research Center subject. All right, Mark, please.
Thank you so much for the nice introduction, and thanks for coming to my seminar. I promise I won't keep you out, keep you beyond sunset, so you'll be able to go trick-or-treating. And thank you to Chris for having me here. It's a great pleasure. So when I went to the Naval Research Lab, there was a push to start moving density functional methods into chemistry, and I had worked a little bit on molecules for my thesis, and so that kind of became my duty for about 20 years, was to push the envelope on density functional theory for molecules and clusters to the extent possible. And for those of you that might be considering a postdoc sometime, the NRC has these great programs where you can go to labs, DOD, NIST, and be there for 2 years to pursue whatever you decided you wanted to push for that 2 years. They're the National Academy of Science NRC postdoctoral fellowships, and it was really a nice time to be able to do independent research. As long as I was trying to do large-scale calculations, they really let us do whatever we wanted at the DoD labs. It's a little bit more informal working environment than the DOE, and of course it takes all kinds of paradigms for success in science. So my job was to try to do large-scale calculations, and little by little I got interested in how to include vibrational modes within density functional theory, how to incorporate spin polarization and magnetism into density functional theory. And about the time I went into program manager, I was really trying to work hard on field-induced electron transfer. And possibly that's going to be a place where efforts will be returning due to the CHIPS Act. We'll have to wait and see. But one of the things you realize when you actually start writing codes is that regardless of whether you're talking about quantum transduction or light-induced electron transfer, field-induced electron transfer, the ingredients that go into the calculation are pretty much always the same. And it's just a matter of figuring out how to black box calculation of dipole matrix elements and what have you in a way that allows you to shift gears depending on what you're interested in. So this happens to be an experiment that was being done in the biomolecular physics lab at NRL. They actually decorated a virus with gold nanoparticles, and then and it was an icosahedral virus, so you can actually look at this C60 molecule and think about each one of those purple blobs becoming a gold nanoparticle with space for the bonds to put this this molecule in between these two surfaces. And then if an electronegative analyte comes along and docks with the phenyl group, the conductivity changes. Okay, so that was one thing, and then we worked on molecular magnets, and there's two types of molecular magnets, and most of my talk will be on that. But what the field was doing was to first look at these molecular magnets that have three metal ions, usually spin 1/2, arranged on a perfect equilateral triangle lattice, with ligands surrounding that triangle to hold the triangle in place perfectly. That's one type of molecular magnet, and the other type is shown here. This is the iron 4 molecular magnet, and it's tethered to a graphene substrate. So you know, the field of molecular magnetism actually was discovered by people that were trying to make the oxygen evolving complex or for water splitting, and it requires you to be able to calculate spin-orbit interactions, basically. So we want to do this with density functional theory. We'd like to do it with even more accurate quantum mechanical methods, but there's certain issues that arise within density functional theory that there's an error in the LUMO level, or the Fermi level, whichever language you speak, in DFT, and it's system dependent. So there's always going to be a mismatch between the HOMO on one site and the LUMO on the other site, and as a result, when you try to simulate a molecular magnet on a surface, you may get fictitious charge transfer. And what I'll try to convince you of is that as long as we get the electronic structure qualitatively correct in these molecules, we can describe their magnetism, but all bets are off if we get fictitious charge transfer from the lead to the island. So that's one problem, misaligned Fermi levels. The other is that there's overestimated spin excitations. And what that means is that, you know, there's an energy scale for two spins to be anti-ferromagnetically aligned, and there's an energy for them to be ferromagnetically aligned. The good enough Buchanan-Mori rules tell us when to expect ferromagnetic to be energetically preferred relative to anti-ferromagnetic. And because of the fact the d electrons, well, all the electrons in a DFT system are a little bit more diffuse than they should be, you end up overestimating the kinetic energy penalty from going to here to here, and you get overestimated spin excitations.
How much usually?
Usually a factor of 3. So there's sometimes when you miss the sign,
Right.
but usually you get the sign right. Usually you're off by a factor of 3. Okay, so these are some of the issues that were around and are that people would use something known as the Hubbard-U approximation to try to fix. And I'll be saying a little bit about a methodology that I've been developing in terms of the self-interaction correction. So just to give you an idea on how you do these calculations, suppose we wanted to do a calculation on the benzene molecule. What we would do, conceptually anyways, there's always details under the hood, we would take Gaussian functions of variable length scale, largest one being something on the order of 100 times z to the 10^3, and the longest range one being on the order of 0.01. And we'd place it on each atom in the molecule. And then we would expand our wave function in terms of these shape functions with these unknown expansion coefficients. And then it's sort of a standard, very similar to the way you do the Stark effect. You reduce trying to solve Schrodinger's equation to a matrix which you have to diagonalize. And then you get the wave functions. And you kind of go round and round in circles here. You start with the density. That gives you the Hamiltonian, which gives you the wave functions, which gives you the density again. And you self-consistently solve this problem until the output density is the same as the input density. So one of the things you have to be able to do is numerical integrals. And I just illustrate here what our mesh looks like. You can't use spherical coordinate system. You can't use rectangular coordinate system. But anybody who's ever sliced a cake knows that it's possible to slice the cake into little boxes. And if you make those boxes small enough, there's always a strategy for being able to do integrals inside each box. So you can kind of see that there's spherical coordinate system inside these boxes and non-uniform grids outside, and that's pretty important from the standpoint of being able to do these things quickly. Now, the thing that we always learn in physics and chemistry is that there's spin up and spin down, but the thing we always have to remember is that spin up and spin down could be this way, it could be that way, this way, what have you. And the spin-orbit interaction actually determines whether you define your axis of quantization to be in this direction or this direction. And so Van Vleck explained to us that by looking at the energy as a function of the orientation of the axis of quantization, you can find magnetism. And his work was done in, I think, 1934 at the University of Wisconsin-Madison. And he did it for the nickel solid and showed that the energy along the 111 direction, the spin orbit energy, was different than the energy along the 100 and 110 direction. And that's the origin of magnetocrystalline anisotropy. And the same would be true for a molecule.
Please, can you please repeat what you said about the spin slow something or whatever?
Okay, well, yeah, so let me do it this way. So, I mean, this of course doesn't have any spin, but suppose we took the electrons away. Then if I put the axis of quantization this way, the spin orbit energy would be different than if I put it that way.
Uh-huh.
And the difference of those two energies is the magnetic strength.
Are you using the fact that the molecule is planar and the other is perpendicular to that?
Well, the way the calculation's actually done is you just put in the coordinates and you get out an equilibrium geometry. it depends on the user's choice as to how they've defined X, Y, and Z axes. And then you calculate the spin-orbit interaction, and you get a tensor, actually. And you diagonalize. It's just like diagonalizing a moment of inertia tensor. So, right? So yeah. So if you think about the moment of inertia tensor for this, well, one's going to be this way, and then there's going to be two that are degenerate, right? And same thing will happen if that was a magnetic system and you were calculating the spin-orbit energy as a function of orientation. Okay, so again, there's two types of molecular magnets. One that I still call molecular magnet, and one that I used to try to call a spin system. And the difference is that the ones up top tend to have a large number of unpaired spins per metal ion, and the ones at the bottom usually have just a spin 1/2, one unpaired electron per metal ion. The reason that's important is, in this case, there are no 1 or 2 electron excitations that couple to the ground state. Whereas in this case, both 1 and 2 electron excitations would couple to the ground state. And so here, you really need a multi-configurational methodology to determine the electronic structure and the magnetic effects. Whereas here, you can do what Van Vleck did, and just think in terms of a single determinant and determine the energy as a function of the axis of quantization. In this case, we have we have 20 unpaired electrons, so the total spin is s equal 10, and the ground state has 21 different energies. Well, actually, one one-fold and 10 two-fold energies due to the spin-orbit interaction. And in this case, there's really nothing interesting that happens on site because it's a spin 1/2 unpaired electron, but it's interactions between determinants that differ by 1 electron that define the behavior. Okay, so how would we go about doing that? This is, again, the case where you have 1 unpaired electron on each metal ion, and you have to couple it to a Heisenberg Hamiltonian or an Ising Hamiltonian. And so you can start the calculation with a certain spin ordering by creating some sort of biasing field on each atom. And then you get a different energy for each ordering. In principle, there's 2 to the 15th different orderings, but in this case. But in practice, there's about 12 or 13 orderings that are relatively low energy, and each one of these would have 12 other orderings that are related by symmetry. And so it's not that hard to back out the Heisenberg Hamiltonian for this structure and then diagonalize it to get the spin excitation function. And this spin excitation function was multiplied by a factor of 2.7 to agree with experiment. Yes?
So I have a quick question. So is your spin quantum spin or classical spin?
Well, we're calculating them within density functional theory. If you look at all those arrows, that would be the starting potential that we would use. We would do the calculation, and then we can calculate the moments on each atom and see whether or not that's really the spin ordering we wanted. Regardless of whether it's what we wanted or what we got, it's still a piece of data for parameterizing this Hamiltonian. So by the time there's a little bit of hocus pocus here, but generally speaking, what people do is they back out these J's from the energies, and then you diagonalize that, and you get multi-configurational determinants that give you this spin excitation function. So it's kind of a second quantization, very similar to what you would do when you calculate the spring constants for vibrational modes. But there could be improvements here. But this is maybe starting to be a little old-fashioned by today's standards. Okay, so now if you do that for the...
Before you go, looking at your experimental data, I would say for temperature below 100 Kelvin, your experiment and DFT looks pretty good.
Yeah.
So is 100 Kelvin related to average J in your Jij?
Well, the point is that these J's in this particular case conspire. These, in this case, these are actually second nearest neighbor vanadiums.
Okay.
So the exchange coupling in this region is actually due to the couplings of the metal ions to the north and south pole, not intra-spin coupling on the equator. And so what that means is that these couplings are really what you would expect from the good enough Kanamari rules, and these are a little different. This is actually a relatively unusual situation. So when I say that I should multiply by a factor of a third, there's probably two different factors that I should be using in the low energy and high energy region. And of course, there's no hard and fast rule that this J is really 2.7 times too big, and this one is exactly 2.7 times too big either. It's so you know, we get about the right shape, but obviously there's deviations. Now, if you wanted to calculate the anisotropy in this system, what you'd have to do is take the coefficients of the wave functions that you get out of here, turn them back into real Slater determinants, and then calculate the expectation value of the many spin-orbit interaction. And there would be determinants that differ by, you know, one electron, and so they actually be coupled to the spin-orbit interaction, to the spin-orbit operator. And that would make it very complicated to calculate the magnetic anisotropy for these systems, but turns out it's very, very small, and that it's the spin orbit presents itself in a different way in this case. So what you have to do is consider the fact that there's these upper Hubbard band excitations or charge transfer excitations. You have to be able to calculate the energy difference between the three states that look like this, and three states that look like that, and you have to have the spin orbit interaction between these two terms. And what that does is it takes it gives you a low energy spectrum that has two Kramers doublets separated by a pretty small energy, and then for a J equal 3 half state up above, and then very high energy excitations as well. So this is was suggested actually originally by Loss and Lundberger as a way of potentially getting a qubit, but the off-diagonal spin-orbit interaction is quite small, and you don't get a very large splitting between the two twofold states. When you diagonalize that Hamiltonian, you kind of get block functions that have dipole moments pointing up, and then 120 degrees and 240 degrees. And the spin 3/2 manifold is not chiral, whereas the two spin 1/2 manifolds that split because of the Jelsinski-Mariah interaction are eigenstates of the chirality operator. So so you get two states, and you can start thinking about trying to drive to control the spins by application of an electric field. And that's what the spin electric coupling was. It was finally.
Before you go, yeah.
Yep.
So, do you have some kind of quantitative number of electrical field? How to drive the transition? Roughly, how big a field it should be?
Well, that's a good question, because these are very small energies.
So
I mean, what I do know is that in general, when anyone does an electric field calculation, they're using laboratory fields that are huge compared to the laboratory,
right.
to see very small effects. So let me see if I can.
It's okay. Just curious about.
But yeah, I mean, we've published the dipole moments, so you can back it out from there. But I guess I can't tell you give you a value.
No worry.
Okay. Okay, so now the magnetic anisotropy, and again, just to be a little bit basic, imagine that this is going to be our the way we store memory. We're either going to have a bar magnet that's in a cylinder with the south pole pointing down, or the south pole pointing up, and then if this was going to be your computer, you'd have to run around and pick up the magnet and rotate it. And this would be the way to do it with the lowest possible energy. Yes, go ahead.
Yeah, why the electron with spin up is unhappy?
I'll get to that in a second. If you stand on if I drew it right, it would be that if I rotated it, the smiles would rotate too, but that's beyond my artwork. Okay, so let's think classically for a second. This is going to store 1, and this is going to store 0, and we want to switch from 1 to 0. So we very carefully pull the thing out of the cylinder, slide it across the table, and turn it over. And that's the energy it would take for this binary bit. What Van Vleck said is that, look, when an electron is moving through electric fields, it thinks it sees a magnetic field, and that's equal to the velocity operator crossed into the gradient of the Coulomb potential, or the electric field, in other words. And as a result, if the magnetic field is going this way, the spin-up electron is going to be unhappy, whereas the spin-down electron is going to be happy. And on average, their energy isn't going to change. Now, this cartoon stops short of the point that, generally speaking, in a magnet, the first order energy is not relevant to the magnetic anisotropy. They cancel one another out, and it's the second order effects that really lead to the magnetism. If you have a molecule that's shaped like this, if you have, in Van Vleck's case, where he had a cubic crystal, it's not until you get to fourth order, in other words, 1 over the speed of light to the 8th power, that you start getting magnetism. This is 1 over the speed of light to the 4th power for these systems. So density functional theory generally does not get the right gap, but I do have a review article from sometime around 2006 where I went very carefully and to try to look at two things. One, that you don't have to screen the spin-orbit interaction, and two, that that you don't have to include higher excitations. And what I found for this, this was kind of the first molecular magnet, manganese 12 acetate. You get very, very good agreement with experiment, and you should sort of expect that, even though it's a small energy, because the reason it's small is it's divided by the speed of light to the 4th power. Okay, so you get very accurate results if the electronic structure is qualitatively correct, and completely wrong if you don't. Okay, so suppose you add an electron to the molecule. There's a couple things that can happen. It could spread out over the entire molecule, delocalize, and if that happens, it turns out that the magnetism gets larger because you're starting to get a metallic system. The other possibility, which corresponds to the experiments that are done, is that in order to add an electron, they have to add a donor, and so the donor is positive, and it influences where the electron decides to go. And if it localizes on one of the metal centers, then the anisotropy goes down. So this is just to say that you can control the magnetism of both types of molecular magnets by adding electrons. Okay. Very quickly, this is the people were a little bit concerned about the accuracy, so some experimentalists in Germany asked us to do the calculation on this system before they had told us what the measurement was. And the fact of the matter is, you just get good agreement. Okay, so I mentioned that if we add an electron to a magnet, we're going to change the magnetism. And so you can start thinking about spintronics, where you have an electron that moves from a lead to the molecule and then back to the other lead. When it lands on the molecule in the middle, it's going to somehow influence the local moment. It might flip, and as a result, when the electron leaves the island, it might flip with the simultaneously change in spin projection of the island. So we've tried to look at this problem quite some time ago, and what we found was that for most systems, when you have a lead, especially if it's a gold lead, the electrons jump onto the island, and you end up with non-integer number of electrons here, non-integer number of electrons here, and non-integer electrons here. And what we really want to do, if we want to simulate some sort of electron transfer mechanism, is start with initial state with one extra electron here, no extra electrons here, no extra electrons here, get to the intermediate state where it's 0, 1, 0, and then finally to the other side where it's 0, 0, 1. And this was kind of the point at which I started thinking that we're probably not going to make much more progress with density functional theory as it stood in 2013. And so what we'd like to do is consider systems like this. We'd like to think about this as potentially being a qubit someday. We want to attach it to a surface, and we want to attach a bunch of identical molecules to the same surface, and then start thinking about how to move moments or spin projections on one of these systems to another. And how we do that is going to depend on how we choose the substrate, whether it might be gold or graphene. Graphene might be better because at least is well matched to the polymers that are attached to the molecular magnet. Okay, so that, there's a lot of interest now in doing high throughput calculations, and so to take this seriously, we want to be able to modify the electrodes to our heart's content, determine how we're going to take our molecular magnet or qubit and attach it to the electrodes. What's the perfect wire, and then we want to determine what metal centers are compatible with with the electrodes and wires that we choose. So all of these problems are plagued by the self-interaction error, and so I'll turn to that next. But so for vanadium-15, the spin excitations are too big. For manganese-12, the concerted spin flip energies, as well as the charge transfer from the manganese to the gold, are qualitatively incorrect. And for iron-4, we actually got around some of the problems, but there's still issues related to mismatches in electronegativity. So somehow we want a theory that hopefully has the speed of density functional methodologies, but not the self-interaction error. And so we're part of a center that's funded by the Department of Energy. And what the sort of systems we're looking at is a molecular magnet inside of water. For those of you that do calculations with DFT and water, you know that if you put an anion in solution, it will donate its electron to the solution, which is generally not the right answer. In this case, we had a negatively 3 charged anion in water. If you kind of do a calculation on the water cluster and the solute that you're about to put in it, you would find that the energy of this trianion was approximately 12 volts higher than the energy of the water cluster. So what that means is you put this chromium -3 compound inside the water, and you get the wrong answer with charge spread out on the surface of the water droplet. The other problem for magnetism is that the most interesting cases in magnetism are when you have a complex orbital at the Fermi level, in other words, a permanent orbital moment. And density functional theory generally chooses the Jahn-Teller distortion in cases where you might be allowed to have one unpaired electron fully occupied at the top of the Fermi level. So again, that's a case where we needed this self-interaction correction, and I'll say a little bit about this graphene aminoferrocene in a second. So
before you leave this, looking at this system that you're considering, 117 H2O, and that many chromium, blah blah. Can you apply your technique to, let's say, 1 H2O and see? You explain everything about H2O with your scheme, or?
So what we showed, and I don't have a slide with me right now, but if you take a water molecule here, and that chromium +3 carboxylate 3, which makes it -3, okay, and you bring them together, the water steals the electrons, and so you actually get a repulsive potential with the water, because the water steals 3 electrons, and then you're bringing 1.5 charges and 1.5 charges together. So it goes up like this.
So this process is well understood by your scheme, that one water molecule and this chromium thing comes in, and everything you can explain.
With DFT, you would get the qualitative, you'd get repulsion. And what you should get is long-range attraction, which goes as 1/4 power, monopole-induced dipole, and then eventually the electron transfers.
Mark, what I was trying to get is a dumb physicist. Do everything reductionist. Take the simple cases, do understand how they react, and then worry about 117 of them.
Yeah, so we certainly did that calculation. The fewer water molecules you have, the worse it gets.
Oh, worse.
Yeah. So because you get some stabilization due to charge-induced dipole interactions. So here at the DFT level you get 117 stabilizations, whereas with one water molecule you only get one. So we can't say for sure that if we had an infinite amount of water that we wouldn't have gotten charge transfer, but I think generally speaking, most people would say that you'd expect to get the wrong qualitative behavior. So these the other point that I want to get to is that to have a good magnet, I showed you a bar magnet at the beginning. You really do want to have something that's qualitatively equivalent to a bar magnet, which is to say you don't want you want either 3-fold symmetry, 4-fold symmetry. 5 would be okay, but I've never seen it happen. In order to get a good magnet. And so one of the things you have to worry about when you, in addition to the fictitious charge transfer, when you start putting molecular magnets on substrates, is that the substrate could have a different symmetry than the molecule you've defined. And so what I've been realizing is that chirality is somehow capable of doing a compromise and restoring the symmetry of systems, and I'll try to say a little bit about that in a second. So self-interaction correction. Again, I actually worked on this as a graduate school student, and the last day that I was leaving Madison, the postdoc that I worked for brought in a paper, which I'm almost positive he didn't show me he was waving it around like this, and it was about the Fermi hole. And the Fermi hole is basically if you square the Fermi hole and put in the Coulomb operator and integrate over all space twice, you get the exchange energy. And so to account for the self-interaction correction, there's kind of two pictures. There's a picture of localized orbitals that are used to actually fix what's wrong with the exchange correlation potential. And then there's the canonical orbitals, which remain the electrons that are more or less observable. And so we had defined something known as localization equations to solve the SIC problem that actually Purdue and Zunger had published in 1981. And so after about 4 or 5 years, I was getting ready to go to NRL, and Rick Heaton was also going to work for the Navy in a different capacity, and he had found this paper by Lukin. I'm pretty sure that's who the author was. And it's a very simple procedure that you can define these Fermi orbitals, as shown down here, where you just pick a position for each electron and put the density matrix in the numerator and the square root of the density in the denominator. And if you think about that, if this was a complete sum over states, the numerator would become the delta function, which would of course be very localized, and the denominator would become the square root of it. Let's see. That would it'd become 1, I guess. So you can imagine that for n electrons, you're going to get, I don't know, some percentage of a delta function at each point you choose. And then there's a technique known as Lovedean's method of orthogonalization, where you can, given a set of orbitals that you get from anywhere, you can orthonormalize them in a way that, in a least square sense, they look exactly like the, very close to the original orbital set. So in 2014, in collaboration with Adrian Rosinsky and John Perdue, we developed this new way of accounting for the self-interaction correction in density functional theory, and we've been pushing it as much as we can for the last coming up on 10 years, I guess. And one of the questions is whether or not there is always a solution. It turns out there is. Prior to a year ago, November, we had only found 3 solutions for the lower half of the periodic table, but then we found a trick and found solutions for the rest of them in 36 hours. And it's actually related to the Kramers expansion of determinants, which I can tell you about sometime if you're interested. But in any case, we have this method now for improving the density functional theory. So far, it's not running at the speed that the PBE functional works, but for any electronic system you choose, including the free electron gas, you can find localized orbitals, and you can find one localized orbital for each electron. And now think about when we learned about 1A functions, we learned that 1A functions only work for insulating systems. So this is a technical detail that a group at Central Michigan University, UTEP, Tulane University, University of Pittsburgh, and Florida are working to try to fix. And I think I won't go through the formulas. So now now we at least know our way forward from the standpoint of being able to get a qualitatively correct electronic structure of a molecular magnet on a surface, so we can go back to our hope of finding the perfect lead. And so many people think graphene might be a good lead for assembling qubits. I just want to point out that if you do a vibrational calculation on a graphene flake, first off, you will find that it's vibrationally stable, but you'll also find that regardless of how big it is, it can form a sphere, and the energy to form that sphere is approximately 20 volts, regardless of the size. And that was something that David Tomanek pointed out right at the beginning of the fullerene craze, and it's related to the fact that you're always adding 4. When you close it, you're adding the equivalent of 4 new carbon-carbon bonds. I hope I'm remembering this correctly, and then that brings the energy down, and then the if you think of it as a piece of rubber, the energy pushing it back up is just due to deformation energy, and it's a constant. So this molecule is no different, but what we looked at it for this system was whether or not there'd be dangling bonds antiferromagnetic behavior on the edge states, and we calculated the spin excitation spectrum. Okay, so now we have our substrate, and the question is what do we do about the fact that the symmetry of the molecule we want to use for the information unit, the energy collector, what have you, is inconsistent with the substrate. So just to take an extreme example, imagine if you had a bunch of four-fold coordinated phthalocyanines and you wanted to layer it on graphene. Well, graphene has this six-fold structure, and six-fold and four-fold is certainly incompatible. But what you can do is you can do these moire patterns, get a much larger six-fold parameter that now at least the little quantum wells, or whatever you want to call them, are allowed to will accommodate a molecule of that size. And then when you put the molecules down, rather than put them all down commensurate with one another, as you go around a hexagon, you rotate each molecule by 2 pi over 6, and then you end up with a surface that is chiral, but also compatible with the symmetry of that surface, with the loss of packing, obviously. So I guess you have to take the good with the bad. And I just wanted to run through recent example where we think we might have succeeded in doing that. An experimental colleague of mine, Ahmed Al-Ghendi, in collaboration with a synthetic chemist, they started out with ferrocene, which is one iron between two 5-membered rings. And then in the gas phase, they exposed it to both sulfuric acid and nitric acid. And they believed that they created aminoferrocene. Aminoferrocene would be one hydrogen replaced by an NH2 group. And sorry, I didn't. Do I not have a picture of aminoferrocene? Maybe I don't. Okay. And then what they found was extremely large magnetism, room temperature magnetism, which is not necessarily surprising, and I'll say why in a second. But the largest magnetic anisotropy of a molecule, prior to this, I think is below 100 Kelvin. This was up in the neighborhood of 300 room temperature, so 340 Kelvin or whatnot. Now think about two pentagons with a iron in the middle. First off, the way to think about that is that the iron has taken on a krypton sort of electronic structure, because you have five dangling bonds on the top, 5 dangling bonds on the bottom, 26 electrons in the iron. All those 5 plus 5 electrons fill the shell of the iron, and it's very well known that ferrocene is stable and magnetically inert. So his idea for replacing a hydrogen by an NH2 was that he thought that he could then withdraw some electrons from the iron, and then when he placed it in close proximity to graphene, he thought that maybe the graphene could steal some electrons as well. Certainly, anytime you put system A and system B together, you have the possibility of either system B stealing charge or system B adding charge. Either one of those scenarios would cause magnetism, because now you're talking about open shell systems. So what I show here are the magnetic anisotropies of the +2 ferrocene varieties, which are very hard to make. And what you find are, anisotropy energies that I've never seen before in any other molecular magnet, 500 to 600 Kelvin. And so I think that's an indication that whatever they did in their experiment, that one might be able to get extremely strong magnetism. The issue, of course, with this ferrocene is that it has a 5-fold axis, not a 6-fold axis. And then again, if you add this NH2 to it, you break the symmetry. And as soon as you break the symmetry, you get a Jahn-Teller distortion. And as soon as you get a Jahn-Teller distortion, what you do expect is that the anisotropy should go down. And that's what the lower panel shows. So you can just look at these 500 to 600 Kelvin results versus the, let's say, average of 7 Kelvin results for various ways you can put one ferrocene on graphene. But that doesn't necessarily mean you can't get strong magnetism here, because you should have the trifecta of magnetism, which is the on-site magnetic anisotropy, the shape anisotropy, which probably is very small in this case, but then you also have, in this case, coupling between the metallic electrons that are running around on the graphene and the ferrocene, which is a much larger coupling, RKKY coupling, than you expect from the good enough Kanamari rules. So there's possibilities to get large magnetism by having strong exchange energies between weakly magnetic systems, or large magnetism by having high symmetry magnets.
And these numbers are calculated numbers or experimental?
These are calculated numbers. And it's known that this is strong. Okay, one thing about DFT, see, I have strong magnetism for both the +2 state and the +1 state. And the reason that happens is that there's a 2-fold and a 1-fold state in the ferrocene, and if you take this electron off and that electron off, I've taken two electrons off, then I leave behind a pi state, a px plus ipy state, complex state, which has a permanent orbital moment. So that's the case where we absolutely think we're going to get a strong magnet, because we have a permanent system. In DFT, what happens when you take one off is that as you try to empty the one fold, it shifts down and becomes accidentally degenerate with the 2-fold. So, and this may be an artifact of DFT, but as a result, for the +1 state in DFT, you still get these partially, well, you get 3-fold degenerate partially occupied states, and still very large anisotropy. So we want to do this with SiC, and that's where we're headed. But what we were trying to do was put these systems down perfectly with oxygens or hydroxyls axially above the pentagons, and it almost works when you use the self-interaction corrected method, But what we found is that if we place if we make a 6-membered ring where we kind of rotate the molecule by 2 pi over 6 each time, we don't completely have these dipole moments repelling one another, and we still get charge transfer from this ring to the graphene. The graphene Fermi level remains the same, but just keeps accepting a few electrons. So we believe we get RKKY exchange coupling here with a low anisotropy system, and each one of these molecules is now bound to the graphene by 3 volts, which is really pretty big. And
the red is not magnetic moment, it's
right,
electric moment, dipole moment.
Yeah, it's the dipole moment. There's the orange that you can see behind it is the iron hiding between the 2 layers, trying to escape, but it actually can't. And then the oxygen is the one that's keeping the iron open shell. And so you have electric dipoles interacting, and you have open shell structure on each iron, and probably RKKY coupling between the different magnetic units, which
What's
could
the implication of the geometric phase?
You mean other than the fact that
You're coming back, but you have
well, okay, so we don't want to have transverse anisotropy. Because if we have transverse anisotropy, then you get very rapid resonant tunneling and magnetization, or you very rapid loss of magnetism. And so if we don't arrange them to be commensurate with the symmetry of the substrate, we might have strong magnetism, but not something we can instantaneously switch with the magnetic field. That's where we're trying to get to, and perhaps I'll just end with an exam for the students, if you don't mind. Which theoretical approximation is qualitatively different than all the others? Hartree-Fock, multi-configuration self-consistent field, non-relativistic approximation to Schrodinger's equation for a hydrogen atom, the DFT approximation for quantum mechanics, or Newton's equations for planetary motion? It's a trick question.
I thought neutrons were different.
Pardon?
I thought Newton's equation should be different.
Yeah, it's a trick question.
No, I heard you.
Anyone else think Newton's equation is the odd theory out? Could be, but the point is that if you read this paper by Purdue, this is the first DFT, and if you look, it's always good to read the last 2 paragraphs of the paper. And what he states in here, and I think his co-authors also had this opinion back then. I'm one of them. But the point is that the long-range behavior of density functional does not go as 1 over R. And you need to have self-interaction corrections or weighted density approximations to achieve the 1 over R behavior. So the answer is that DFT is the one that doesn't fit into the rest of these categories, because as implemented, it has a qualitatively wrong long-range attraction, and at the same time, it's somebody publishes a paper using DFT, I think once every hour. It's good to understand when you need to have that asymptotic potential correct and when you actually don't. And And one thing you can think about as to why it might not always be necessary is because if you're in the asymptotic region, there's no electron there to observe it. So, so anyways, I think I'll stop and hope that I gave you some idea on how we're trying to slowly get to the point where we can simulate molecules on surfaces, simulate how to selectively address one molecule, even though it has a bunch of neighbors that are nearly identical to it, and to properly design the magnetic behaviors. And part of the need is to keep working hard on this self-interaction method. And with that, I'll take questions if there are any. Thank you. Sorry to keep you over. So.
Thank you very much. Yes.
You know, your number 3 over there, the Schrödinger equation, the non-relativistic approximation, is the only two-body system. Everything else is multi-body. So this clearly
that's wrong.
is not reality.
So, do I still get partial credit?
More questions? All right. Students still own him the answer, right? So yeah, go ahead.
I have a general question. I like to learn that although the electrons have a happy and unhappy state depending on the spin, they both balance out to have a neutral mood. So that's interesting. But like I say, I just want to learn, like, so all this work, so just to zoom out, I'm an astronomer, so I don't know anything about this. So like, what are the direct implications of this work?
Oh,
to materials or
so,
yes.
So the reason this was originally interesting was curiosity, because you have these high spin molecules, and you have cases where they split into an upside down parabola, and you can hold the magnetism in one orientation for a month, and then if you apply just the right magnetic field, it flips immediately, and that magnetic field is proportional to the second derivative energy, which is called the anisotropy complex. So when the first magnet came along, people were excited that, you know, in a year from now we're going to have 600 Kelvin magnets, and the only way that's going to happen, I think, is whether we can go down into the lanthanide row and do the same thing. You can in principle get large anisotropies with the 4Ds, but their the exchange coupling is 0. So the practical application will be if we can assemble them and make molecules that either have strong classical magnet but very low density rare earths, or possibly still in the 3D row, we use them for qubits.
So what is the current status of kind of among molecular magnets the best for application, for example, long relaxation time?
I think homium is
a good one?
Yeah.
Somehow, yeah, favorite element. Yes.
So that's one of the reasons we're trying to. I mean, sorry to turn every question back to the self-interaction correction, but
right.
In the lanthanide row, you only get three of the atoms qualitatively correct with density functional theory, because you don't have the right F valence.
I see.
There, and so that's we're working on that, and we've done calculations on single lanthanide molecular magnets, but right now it's a lot more expensive.
Right. Yes,
Yeah, I'm curious about your computational procedures, something you elaborated on your second slide. And you mentioned you include the electric field and the magnetic field. And I'm wondering how do you incorporate the electric field and the magnetic field in your calculation?
Mm-hmm.
And also, you mentioned to get calculated the energy. How about the electric enthalpy and something like electrical enthalpy or free energy?
So that would be the 1/2 E squared term, or what?
It's E times P.
Okay. No, that's in there. So the way we do the electric field is we just put E dot P, and or E dot R. Let's say you could do either, and we do E dot R, and so when you calculate the potential, you just add E dot R to the calculation. And that gives very, very good polarizabilities if you do it that way. If you do it sum over states way with an electric field, you're off by a factor of 5 or 6 due to screening. And the magnetic field we've only done recently. There's a paper by Bifocral Islam and Kushantha Withanaga and myself on because you have to use a non-collinear code at that point. But it's the same thing. We just have B dot S in the potential and B dot L.
So that's Zeeman terms.
Yeah. Yeah, and we use R cross P rather than L because it's Cartesian is better as soon as you have more than one atom. So but I thought maybe by electrical entropy, I've always wondered if there should be like the E squared plus B squared term somehow added as well. Because do you have any thoughts on that?
Oh yeah.
Okay.
All right, let's thank Marker.
Thank you. Happy Halloween.
Yeah.